first, let's complete the part A. Part A, we have a few topics we need to complete. Probably second half we can start part B. Yeah. First half we can complete the remaining part of part A. All right. So we complete this slide last time. So we derived the formula, derivative formula for Fourier cosine and sine transforms. Yeah. So the very simple, very straightforward. All right. Yeah. So next, we can apply these two formulas. We can get a Fourier cosine sine transforms of second derivatives. Yeah. Similar to what we did for Laplace transform. Yeah. Second derivatives. All right. Yeah. What's wrong? A remote control. Doesn't work. Doesn't work. Yeah, let me restart the. Oh, freezed. My PowerPoint slides freezed. Yeah. Let me restart PowerPoint slides. Yeah. Not computer. PowerPoint slides first. This one. Yeah. So quit there. Share again. Then all right. But I need to check remote control. Yeah, it works. Yeah. Restart, it works. All right, yeah. Yeah, so the next slide, let's apply these two formulas to the second derivative. Yeah. All right. Yeah, so here, these are two formulas. When we do the second derivative, we need to do for two versions, cosine version and a sine version. All right. Yeah. So here, let's do. So we copy the two formulas for the first derivative. First derivative, you can see, for the Fourier cosine transform, we need to use Fourier sine transform in its result. There, for the Fourier sine transform of the first derivative, we need to use the Fourier cosine in its result. Yeah. All right. So this kind of cross usage. Yeah. All right. Now let's look at the second derivative. Second derivative. Yeah. So we apply the first formula, and we treat second derivative as the derivative of the first derivative. Yeah. So the first round, yeah, in the formula we have the first derivative as the original function. Then we apply the second formula another time. Yeah. Yeah. Then, after the second time, you can see we only need to use the Fourier cosine transform. Yeah. Cosine, cosine, yeah. So the same type. Yeah. Similarly, yeah, yeah, for the Fourier sine transform of second derivative, yeah, the first time, yeah, cosine, first derivative. So another round. Yeah. So then oh, sorry, yeah. So we have these two formulas. All right, yeah. So at this point, we have these two versions. Yeah. But we have these formulas. But later you will see in most of our applications, we will combine these two, Fourier sine cosine, to one Fourier transform. Yeah. Otherwise, every time we need to calculate two transforms, right? Two transforms, intertwined, mixed, yeah. So that's not very convenient. Yeah. So the more convenient way, we want to integrate these two transforms into one unified formula. So that's the Fourier transform. Yeah, combine Fourier cosine sine as one Fourier transform. So that's more convenient. But in that way, we need to deal with complex numbers. Yeah. So we have to get used to calculations of complex numbers. Yeah. So now you will see in a lot of calculations, if we use complex numbers, it is very convenient. Yeah. All right. So next, let's calculate one example, Fourier cosine transform. Right. Find the Fourier cosine transform of f function e to the negative ax. Yeah. A very simple function. Yeah. So let's, yeah. And when we calculate Fourier cosine transform, remember, we can use the derivative formula. Although here, in this function, you have no reason to use the derivative, right? You have no reason to use derivative. Yeah. But after we see the derivative formula, you can see it is useful if we apply the Fourier cosine transform on the derivative of the function. So we can easily calculate the Fourier cosine transform because we only need to solve algebraic equation. Yeah. All right. Yeah. So let's look at the calculation. Yeah. First, we take double derivative on the original function. Yeah. Now let me ask you, why here we use double derivative? We do not use the first derivative, second derivative. Why is in this example it is more convenient to use second derivative, not the first derivative? Yeah. The answer is very simple. If you look at the forms of the formulas, you will see it is more convenient to use second derivative formula. Why? Because for the second derivative, when we apply Fourier cosine transform, in its result, we also use Fourier cosine transform, right? Yeah. If we use the first derivative, then in the result, we need to use Fourier sine transform. Yeah, but the question does not ask us for Fourier sine transform, right? Yeah. Yeah. So you bring up a new transform, unrelated new transform. So you need to calculate these two, both. You need to calculate both Fourier cosine transform of f function and also Fourier sine transform of this function. You need to calculate, two versions. Excuse me. But if you use second derivative, the Fourier sine transform is not involved. Right? Not involved. All right. Now, let's apply the formula. Yeah, that's the formula we want to apply. All right. So the left-hand side, based on the formula. Yeah. All right. Yeah. So that's we just you know. This comes from the above formula, right? Yeah. We just rewrite. Yeah. You know, we switch. Rewrite it. Then we apply the formula. Take out the constant part, a squared. Yeah. Inside, sorry, right-hand side, let's apply this formula. Yeah. All right, this one. Then, in this equation, we can solve for Fourier cosine transform. Okay? We can solve it for Fourier cosine transform. Yeah? By algebraic calculation, we can find the answer. See? Yeah. Yeah. So we do not need to bring up the Fourier sine transform. No. But if you, so you can try the first derivative version, because after you apply the Fourier cosine transform on the first derivative, you get a Fourier sine transform. So you need to apply Fourier sine transform to get a Fourier cosine. So you get two equations. So you solve those two equations for Fourier cosine transform. Yeah, that will work. Yeah, but you need to solve two equations. Yeah. So in this way, you only need to solve one algebraic equation. Yeah. All right. 8.3, complex form of Fourier integral. Now, we need to really prepare ourselves for complex numbers. All right. From cosine sine forms to complex form. Yeah. All right. Start from the Fourier integral. We have two versions of Fourier integral. Fourier cosine integral, Fourier sine integral. Right? Yeah. Yeah. Or cosine part, sine part in one integral. Yeah. Yeah. Fourier cosine sine, that's for the even odd functions, right? Yeah. For even function, we have Fourier cosine integral. For odd function, we have Fourier sine integral. Yeah. All right. Yeah. So here, given a function, given an arbitrary function, can you decompose this arbitrary function in sum of two functions such that the first function is even function, second function is odd function? You do decomposition. Yeah. So this simple fact sometimes is useful. Yeah. Yeah, because in general, our function may not be even function, odd function. So the arbitrary general function is non-even, non-odd function. But even that, so here we have arbitrary function, f of x. Now we want to decompose it. f1 of x plus f2 of x. Okay? Yeah. And f1, we want to make it even. f2, we want to make it odd. Yeah. So then, when we apply formula, so even function, we have even function formula. Odd function, we have odd function formula. Yeah. Things like that. Okay? Yeah? Yeah. It's also interesting. All right? Yeah. Is it possible? There is a simple way to do it. Simple way to do it. All right. F1 function. Think about if I use 1/2 of f of function plus f of negative x. Is it even function? F function plus f of negative x divided by 2. That's even function, right? Yeah. You check the definition of even function. F2 1/2 f of x minus f of negative x. Is it an odd function? Odd function. You check the definition of odd function. Okay. Yeah. Oh, 2 students join us. All right. Let's see. Yeah. Christian. Yeah, Christian. All right. From 2 places. Oh, no remove. Yeah, I want to admit. Yeah. I want to admit. All right. All right. Yeah. Right. Adding together original function. Right. Yeah. So this is structure. So you can see a simple way. So we can do the decomposition. All right. Yeah. So let's recall. So this is our Fourier integral formula. Yeah. We need to calculate capital A function and a capital B function. All right. Yeah. All right. But one thing you need to be careful. Yeah. When we calculate the integral, yeah, when we calculate capital A function, capital B function, our integral limits from negative infinity to infinity. But when we calculate, try to represent the original function in the Fourier integral, our integral limits from 0 to infinity. Yeah. It's different. Yeah. Half axis and the whole axis. Yeah. All right. So now, plug in, right? Yeah. So, we copy the A function integral expression and the B function integral expression back to the, function representation formula. Then, inside the brackets, you can see that's the cosine or sine. Yeah, because same cosine, cosine, sine, sine. So it should be cosine. Cosine of sum of angles, right? Sum of angles. Plus, yeah, plus difference of angles, right? Yeah, because plus corresponds to the difference of 2 angles. All right, so equals cosine of difference of 2 angles. Yeah, cosine. Yeah, so that's the formula, the basic formula. All right. Yeah. So here you can see we can represent the f function, and we use double integral. Double integral here. Double integral. Look at the integral dummy variables v and w. Yeah. V variable in f function. Also here v variable and another variable w variable. Yeah. X, we treat x as the parameter. Okay? Yeah. When we calculate the integral, we can fix that x. Yeah. So double integral. All right. That's the structure. Yeah. Next, let's keep going, yeah, because we want to try to convert this expression, this form, in a more friendly form. Yeah. Yeah. Our goal, we want to go to the complex form. All right, so we are halfway there. We have cosine part. For complex, we need a sine part, sine portion. Yeah. All right. Then, look at here. Yeah. How can we write this formula in this version? Yeah. So what's the difference? You can see, first we extend outer integral, the integral limits, from half axis to full axis, right? Yeah, full axis, half axis. But when we extend to full axis, because we double the value, integration value, right? We double it. So we need to divide it by half, 1 over 2 pi, not 1 over pi. But how do you see when you do that extension, you double its value? Yeah. There is a condition we need to check. If the function to be integrated is an even function, when we do this kind of extension, we double it, right? Only for even function, when we extend from half axis to full axis, because even function is symmetric, okay? Yeah. So when you do that direction, you double the integral value. Yeah. But how do you see the function is an even function? The function here, it's an even function. All right, let's look at the function. This function, this whole integral, is a function of w, right? Yeah. For this whole bracket, the function inside the bracket, when it takes the integral form, it is a function of w. Okay? V is gone, right? Yeah, because it's a dummy variable. After you take the integral, the v is gone. So you only have two symbols, w symbol and x symbol, but x we treat it as a parameter, right? Fix it. We fix x. X is a parameter. So only w is the variable. Okay? All right. W is the variable. All right. Then, so this function, think about, if you replace w by negative w, do you get the same thing? Yeah. It's a function of w based on our definition of even function. If you replace the w variable by negative w, you get the same thing, right? Yeah. So here, you can easily see that. That means this whole function is an even function. If the whole function is an even function, then we just extend the integral range to the whole axis. We double its value, so we need to divide it by 2 to go back to. Yeah. Because in this way, after we double it, we can work on the whole axis, right? Yeah, yeah. Inner integral, outer integral, all on full axis. Yeah. Full axis. Yeah. So more symmetric, right? At least it's more symmetric. Yeah. Yeah. All right. Yeah. So that's the cosine component. Cosine component. Then we also need to look at the sine component. All right. For the sine component, yeah, we just replace cosine function by sine function, we can write the result 0 immediately. Why? Yeah, because sine function is an odd function. Okay? Sine function is an odd function. All right? Yeah. So the part inside the bracket, it is a function of w, right? Yeah, w is the variable. Okay, w is the variable. So think about, if you replace W by negative W, you get a negative value, right? Yeah, think about that. Yeah. Then, so because inside the brackets, this function is an odd function, when we do extension from half axis to full axis, cancel out, right? Positive value, negative value cancel out. So we get 0. So the sine component is 0. But here you need to do not get confused. This point. Here, little f function, both places, little f function is a general function. We do not need a little f function even or odd. No, we don't need it. So it's a general function. Yeah. So the even, odd come from cosine and sine, not from little f. Okay, even, odd come from cosine and sine, not from f. Yeah. All right. Yeah. Now we can combine these two components. Yeah. Sine, cosine component. Yeah. So it's an odd function. Yeah. Sine is an odd function. Yeah. So when we say odd, we need to odd. Okay? Yeah. All right. Then, so we add them up, but when we add a sine component, we need to multiply I. Remember? Yeah? So in front of sine component, we need to add the constant, little I. So then we have this new form, yeah, f of v times e function, e to the I times w times parenthesis x minus v. All right? So we have this complex form of Fourier integral. Okay? Yeah. So this time we get a complex form of Fourier integral. It is also Fourier integral. Yeah. Yeah. All right? Yeah. But a complex form of the Fourier integral. What's the benefit? So you may ask, what's the benefit? The immediate benefit is we only need to deal with one form. We do not need to consider the cosine version and the sine version, because we combine cosine version and the sine version in one formula. So that's the immediate benefit. Okay? So in our calculation, we only need to focus on this e function. Yeah, e function. Yeah. Otherwise, yeah, so if you still use the cosine version or sine version, then in your calculation, it's not very convenient. Yeah. Yeah. Because sometimes when you apply your derivative formula, you get the other form of the Fourier integral, yeah, the other form. Yeah. So that's not very convenient. Yeah. In this way, we always need to use one form, complex form, in our calculation. Yeah. All right. Yeah. So this step. Let's move to the next step. Let's try to understand the meaning of this Fourier integral in the complex form. Yeah. Yeah. Oh, Justin.
So is there no reason then to use the cosine or the sine, or is this just always better? Or
always better.
Always better.
Yeah. So for the cosine, sine, yeah, because you need to do more work. Yeah. Cosine, yeah, when you do some operation, then generate a sine version. Then you work on sine, you generate a cosine. Yeah. So in this way, actually, you double your work. Yeah. So this way, so you only need to work on the e function. Yeah. Otherwise, you need to work on sine two functions. It's here one function. Yeah. All right. Yeah, but another convenience. Yeah, so here we need to compare E function and of sine cosine. E function, it's an exponential function, right? Sine cosine, yeah, not exponential function. So sometimes when you do algebraic operation, exponential function more convenient. Yeah. For example, you have one E term, you multiply another E term, you just add the exponent numbers. But when you do that, you cannot add inside, right? Yeah. You know. Yeah. So, yeah. In algebraic operations, E form also more convenient. Yeah. Yeah. So that's the reason. That's the reason most people they prefer this E form. Yeah. They prefer the E form. Yeah. But for some of the beginners, yeah, because E function you need to adapt your thinking to complex calculation, right? Yeah. So that's something the beginners usually they do not like. They do not like complex numbers calculation. Yeah. Yeah. But for us, especially, we are engineering people. Yeah. So the complex numbers are very important in our problem solving of the real world problems. So we should not avoid complex numbers in our calculation. Yeah. All right. So let's go to the next step. We want to take a closer look at this Fourier integral of the complex form. What's the meaning? Yeah. All right. 8.4, Fourier transform and inverse transform. Yeah. So that's the main topic of this part. Yeah. The title, Fourier transform. Finally, we get to this topic, Fourier transform and inverse transform. Yeah. It comes from Fourier integral of complex form. Yeah. We just derived. So we start with the Fourier integral in the complex form. Yeah. Fourier transform. Yeah. So important in math. Yeah. Start from complex Fourier integral, that formula. Okay? Yeah. So in this formula, we use double integral. Yeah. Inner integral, outer integral, double integral. All right. Then, in double integral, let's look at the structure of this formula. This E function, this special E function we used here, what's that? Yeah. So it has a special role, right? That's that E function. So we call it kernel, right? Yeah. So that E function, remember, we have a special name for it. Kernel. Kernel function. Okay? All right. Yeah. When we define a transform, integral transform, we need to use some kernel function. Yeah. Here, this E function is our kernel function. All right. Yeah. Then, our input function. What is our input function? Original little f function. Input function. Input function, then we use some kernel function. Yeah, we do the integral transform, but we do double integrals, not a single integral, double integral. Then we recover the original function. Yeah? So your input is f function. Then if you do the operation in this way, this special form, your output function is the same as the original function. Okay? Yeah. So that's, we try to understand this formula, the meaning of the formula. Yeah. Input, output the same. Is it useful? Input, output the same. You do not get new information, right? Input, output, yeah. but actually it is useful. Although input output the same, it is useful. Yeah. You need to change your view on this formula to make it useful. To make it useful. All right. So how to make it useful? Think about it. Here we have double integral. Can we split this double integral into 2 halves? Yeah. Because we need to do single integral twice, right? Single integral twice. So then, the first time when you do the integral operation, you get something different, right? You will get a different function, a function different from original f function, right? You get a different function, right? Yeah. Then the second half, you take another integral operation, then you recover the original integral. Yeah. So if you understand it in this way, then you can make it useful. You can make this formula useful. Yeah. Otherwise, if you do not split, basically we do nothing, right? Yeah. We enter input, then generate the same thing. Nothing new. Nothing new. We waste the energy, right? Yeah. We waste our energy. Yeah. But it's not. If you split into 2 halves, suddenly it becomes very useful, extremely useful. Because you can split. If you cannot split, then it's not useful. If you cannot split this formula, then useless. But if you can split, suddenly it becomes extremely useful. A lot of applications we can use this way to solve. Yeah. So let me explain the reason behind it. Yeah. All right. Recall Fourier cosine transform. Yeah. So this way. Yeah. Yeah. But the Fourier cosine transform, remember? Yeah. When we do this, we work on the even function, right? For cosine. Yeah. The general function, we need to use the, both cosine and sine. Yeah. All right. Both sine and sine. All right. Yeah. So here, all right. Yeah. So yeah. So here you can see the definition of Fourier cosine transform. Yeah, so that's the definition of Fourier cosine transform. Yeah. All right. Yeah. Yeah. So here, yeah. So we want to. This is what we did before. Okay. Yeah. So here, yeah. Why we recall? Yeah. Why we recall? Okay. Because we want to understand this formula. Yeah. This is our new formula. Yeah. But we have our old experience. This is our old, the Fourier cosine transform and the Fourier, this is the inverse. Yeah. So this, the first one, Fourier cosine transform. Then it's inverse Fourier cosine transform. Yeah. These two formulas. Yeah. Now we want to connect, make a connection. Yeah, use our understanding of our old formula to understand this new formula. All right. Yeah. All right. So in the Fourier cosine transform, yeah, because this formula tells us the inner integral part. Yeah. So the inner integral part. Yeah. So for the inner integral part, can this full cosine wx, we move it out of the inner integral? Yeah. Because integral, we use the variable, dummy variable v. This term has nothing to do with the v variable, right? So we can move it out of the inner integral. After we move out of the inner integral, then this inner integral part corresponds to the Fourier cosine transform. Okay? Inner integral part corresponds to the Fourier cosine transform. All right. Then the outer integral, yeah. So the result of the inner integral, that's the result of integral. Yeah. Yeah, but we also need, because we move this cosine term out of the inner integral, so it remains in the outer integral. That part, outer integral, is used as the inverse version, inverse Fourier cosine transform. That's our understanding from the old formula. Okay? Now we want to do the same thing on this new formula. Okay? We want to use the same understanding way to split this double integral complex Fourier integral formula. Yeah. All right. Then this E function, can we split? Because there is a Wx part and a Wv part, right? Yeah. First, let's split this E function. E to the I W, yeah, so let me write clearly. Yeah. So that function, let's split. E to the I W x times e to the negative I W v, right? Yeah, split. After the split, this e to the wx, this part has nothing to do with v, right? Nothing to do with v. Can we move it out of the inner integral? Yeah. So the second part of e function, e to the negative I wv, because it contains the v variable, so it remains in the inner integral, right? Remain in the inner integral. Yeah. So in this way, we split into two steps calculating the integral. Yeah. All right. These two steps, then the first step, the inner integral part, we define it as a Fourier transform. How about that? Then the outer part, we define it as an inverse Fourier transform. How about that? So this one formula contains both Fourier transform and the inverse Fourier transform. That's our understanding. Okay? Yeah. All right. So let's write this understanding clearly. Okay? So we have two transform formulas. Yeah. First transform formula, Fourier transform formula. That comes from the inner integral part. Yeah. F hat of W. Yeah. So you use the W as the variable in the inner Fourier integral. Yeah. So you have this E function as the kernel, right? Yeah. E function as the kernel. Yeah. All right. V, yeah, because in our original we use the V dummy variable. Here we replace it by X dummy variable. Yeah. Same thing. Yeah. Dummy variable is not important. Yeah. All right. Yeah. So you get a Fourier transform formula. Then outer, corresponding to the outer integral, you get an inverse Fourier transform. Okay? Yeah. 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 The simple notation F hat. Yeah. Because here, yeah, mathematicians, they use a special symbol notation, that little hat symbol on F function. Yeah. Because the Fourier transform is very important, especially in engineering. Yeah, extremely important. Yeah. So people use it frequently, use it quite a lot. Okay, yeah. So then we should not use some heavyweight, big, complicated notation symbol. Yeah. So we want to use light notation, simple, fast, easy notation. Yeah. So that little hat, very special. Yeah. And typically, it is reserved for Fourier transform. Yeah. Other operations, we should not use this little hat symbol. Yeah, because you get confused with Fourier transform, right? Yeah. Whenever people see that little hat symbol, people always understand that's the Fourier transform. Okay? Yeah. It is reserved for Fourier transform. Yeah. Do not use it for other different meaning. Okay? Yeah. Because you get people confused. Okay. Yeah. All right. Yeah. Yeah. But sometimes people like to use the operator version. This curly f applied on little f, yeah, like a Laplace transform, right? Yeah. So because sometimes here you can understand there are two representations. Okay, yeah, one simpler, yeah, the simpler one, more heavy, right? Yeah, heavier, yeah. But this operation, yeah, sometimes it can help people convey some ideas. Yeah, because this capital F, people treat it as an operator. So in math, there is an operator concept. Yeah, so here. So this notation, yeah, many people like to use this notation. Yeah, there is some good reason. Because people treat it as operator. Yeah. That f, like a function, right? You apply it at a function. Yeah. So yeah, this operator concept, a little abstract. Yeah. Yeah. Many people do not understand the operator concept. Yeah. Let me say some words about this operator concept. Yeah. Yeah. So in math, in many situations, people like to use the abstract concept, operator. It's abstract. Yeah. One abstract. Yeah, I saw some students in homework assignment, they use that operator already. D operator, capital D, differential, derivative. Yeah. Remember in our textbook, there is one optional section talking about D operator represents derivative. Okay? You apply D operator on y function, yeah, that's the same thing as y prime. Okay? Yeah. So this way, that's the operator way. Yeah, just a special form. Yeah. Yeah. So the operator way, in calculation, so sometimes can help people convey some special meaning. Yeah, special meaning. So here, we treat Fourier transform as an operator. Okay? We apply an operator on a function. Yeah. So usually, an operator is applied on a function. Okay? So D is applied on one function, right? D operator is applied on a function. Okay? Yeah. The capital F, the curly capital F, is applied on a function. Yeah. Operator is applied on a function. Yeah. Yeah. Although it has a function. Yeah. So our function, this little f is a function, right? So we do not treat it as operator. Little f is applied on variable, right? Function. So we apply function on variable. Yeah. Function is a mapping, right? Function is a mapping. Okay? Yeah. So you map one variable to, a function. Yeah. Variable to function. All right. And here it's an operator. Operator, you apply an operator on a function, you get another function. Okay? You apply one function to one operator to a function, you get another function. Here you treat it capital D derivative as an operator. You apply the operator on the function, you get another function. Okay? Yeah. So that's the, just the special view, operator view. Okay? Yeah. Yeah. All right. Yeah. So otherwise, yeah, because sometimes when you see the notations, people may get confused. Yeah. What's that? Okay? Why are we writing this way, right? Yeah. Why we represent Fourier transform in these two different ways? Okay? Yeah? So this is a convenient, lightweight way, right? So this is, try to convey some more meaning. Yeah. All right. Yeah. Then inverse Fourier transform corresponding to the outer integral this time. Yeah. So we apply the integral on the f hat, the Fourier transform of the original function. Yeah. Then the kernel, yeah, be careful, the kernel, in the Fourier transform, the kernel has a negative sign, negative IWX. But inverse transform, the kernel has no negative sign. Yeah. So the positive, yeah. E function, e to the IWX. Yeah. All right. Then the remaining form, same, only difference, yeah. Positive, negative. Only difference is on that, the kernel. Yeah. So then you recover. Yeah. So you apply the inverse Fourier transform on the Fourier transform function. Yeah. Then you recover the original function. How good it is. How good it is. Okay? Yeah? All right. Yeah. So these two formulas, Fourier transform, Fourier inverse transform, why it is so important in the real world applications. Yeah. After the break, so I want to spend some time to explain the significance behind these two formulas. Yeah. Why so important when we solve real world engineering problems, application problems. Yeah. All right? Yeah. Yeah. So I can use image processing. Yeah, because in image processing, we need to use the Fourier transform quite a lot, like a noise removal, right? Remove noise. Yeah. Given an image, a lot of noise. How do you remove the noise? Noise removal application. We need to use the Fourier transform, inverse Fourier transform. Yeah. All right. Yeah. Yeah. So after you come back, second half. I talk about this formula, the importance of these two formulas. All right?